So I'm Gary Grider from Los Alamos National Lab. I normally don't give a talk about what I'm going to give a talk about. Normally I'm talking about hardware, but today I'm talking about software. This is a file indexer that we built a long, long time ago, almost a decade ago. And the reason I'm out selling this, this technology is we actually brought in OpenAI to help us with AI in our secure environment. And they were asking the question, how are we going to keep one set of users and another set of users from being able to see the same data, and one set of bots and another set of bots only, they only be able to see the bit data that they're supposed to see and give you the answers from the data that they're supposed to see it and so forth, because if the humans aren't supposed to see everything, neither are the bots. They're not supposed to see everything either. So we needed to provide a way to do this, and it turns out we had one sitting in front of us, and we didn't realize it until we pointed it out. So a little bit of background here. I heard today that I needed to buy an object system to have an exabyte of data. It turns out I've had an exabyte of data for a really long time, and I don't have an object system, so it's not necessary that I necessarily absolutely have to have one, although I understand why people kind of want them. Anyway, we've had exabytes for a long time, 10 billion objects, about 1 billion directories that the objects live in, across many, many storage systems. And we've been living this way for quite a long time. It's interesting because in POSIX trees and other sorts of trees, not only do you have to have permissions to read the file that you want to read, but you have to have execute permissions on the directory structure to get down to the file to be able to read it. So there's two pieces of permissions you've got to pass in order to be able to see a file in POSIX. And if you're going to try to keep bots out of it, you've got to keep bots out of it the same way you would keep users out of it, and that's by obeying POSIX. The GUFI goals. GUFI is a Grand Unified File Indexer. Why do I call it grand? It's grand because it goes across 10 billion things. It goes across 5 or 6 or 8 storage systems, and keeps people to be able to see that the stuff they're supposed to be able to see, and not see stuff that they're not supposed to see. Supposed to enable searches. The idea was for users to call up and say, hey, we think this is broken. It got the answer too fast. And for system admins to not really be able to go get coffee before they got their answers. So one of the ideas was it has to be crazy fast. And the initial design thoughts were, why not just flatten the whole namespace? This is what most products do that do this indexing. And shard it, and you can make it go arbitrarily fast. The problem is the minute you flatten the namespace, you lose the hierarchy. You can't tell where the execute bits are. You can't know whether the person can actually walk down into those bits. And so you kind of have to keep the hierarchy to be able to do this. So how would you get a hierarchy to go fast? If I were an object person, I would have given up and just done a different thing. But a long time ago, we didn't do that. We just tried to solve the problem. So we did in another way. This was some of the initial design thoughts. How does it work? It works by us replicating the directory structure onto a system, another file system. But we don't replicate the files. We just make a little database, and we put it in every one of the directories that basically says, here's what all the files are, here's where all the links are, and all that kind of stuff, and all the information about them. And so you might say, well, gosh, that's interesting. You've replicated the whole tree structure, and basically to keep your POSIX permissions to work, and you've gotten rid of the files, and you just have these little databases, of course. But that's still an awful lot of databases. In my world, it's 1 billion directories, so it's 1 billion databases. So what are we going to do about that? So anyway, this is how it works. Each directory has a database in it, and there are 3 tables in each directory. In each database. One is the directory, the entries table. The entries table is file information. The directory summary is information about the directories, so it's summary information about the directories. And there's a tree summary record or table, which is information about the tree below you. And so there's those 3 tables that are inside of each database. These are the schemas. I'm not going to take you through. It looks a lot like a stat structure, so it's basically all the information about a file. This is the summary table, and it's basically the same thing, except you'll notice that it has all these. The directory summary has all the same stuff, but it also has all this information about. Oh, well, it doesn't work. The total size, the total larger than a kilobyte, total larger than a megabyte. These are basically That's summary information about all the files in that directory. And there's a tree summary table, and that summarizes the same kinds of things for everything below you. So there's one record in each directory that summarizes everything below it. So how will it be fast? If you have millions of directories, each one has a database. That's a million databases. That's an awful lot of little databases to open up. Sure enough, it is. Turns out, if you look at the way people use POSIX trees, almost all the directories below a certain point have exactly the same permissions, or they have permissions that only allow the same people in them. That's the way UMask works in Linux. When you untar something, that's the way it's going to happen. We have an awful lot of old and new stuff. We looked through the entire set of stuff we had, all 10 billion records and all billion directories, and we looked to see how much of the trees are the same from a certain point of the tree down in permissions, and it turns out an awful lot of them were. And so we said, wonder we can use that that fact, the way people use trees, to make this go faster. So what we do is we walk all the way to the bottom of the tree, and then we start walking up, and we check to see if everything below me can be seen by the same people, and if the same people can see it, we roll that information up. And then we do that again and again and again until we get to where that's no longer true anymore, and that's called a roll-up. And so essentially we're taking a whole bunch of little databases and combining them into a bigger and bigger and bigger database until it gets to the point to where all the things below you are the same, but everything above you is a different set of permissions. And so that's called a roll-up, and it turns out that it rolled up so far, our 10 billion things rolled up so far, that there wasn't enough parallelism left to use the threads in a single machine. That's how much roll-upism there is in trees, which is kind of interesting. And so we actually had to stop it at a certain point so that it didn't roll up too far to lose the parallelism. So that's interesting. That's the way roll-ups work. There's two kinds of permissions you have to obey. Again, one is the permissions of the directory, and the other is the permissions of the files themselves, so you have to protect metadata from both cases. How fast is GUFI? GUFI was compared to a cousin of GUFI, a fork of GUFI that HPE did in a product they call Brendexer, which they give away with their Luster product. And you can see that it's a lot faster than that. And the other, competitors, it's really, really, really faster. And so typically users at our site have some numbers of hundreds of millions of things, and they can't pick their copy cup up before they get an answer. It's that fast. Okay, so if I have 100,000s of databases, how am I going to think about this as one database? How am I going to think of this as one table? Because I can't deal with 100,000 databases. I want to do a query against a table, and I want to get an answer. And so GUFI's job is essentially to make whatever query you put in across all this stuff with the subset of things that you're wanting to see, make that look like a table to you. And that's what it does. And it does that in a POSIX compliant way. How do users interact with it? They use GUFI Find, GUFI Stat, and GUFI LS because users know how to do Linux, and that's all they know how to do. But if you were a little more sophisticated, you could dig into it a little deeper, and you can go really, really deep. And so how do we set this up at LANL? Well, we have this thing called /search, which is the top of all the trees. And then we have home and projects and campaigns and scratch file systems. And under each one of those is the metadata tree for all of those systems, all those storage systems. And across that whole thing, there's 10 billion, objects. And so we've got these tables. Again, I talked about the tables, the entries table, the summary table, and the tree summary table. There's a bunch of functions I won't talk about yet. Here's some example data. So I just made a little tree. I run this on my Mac because I don't find that the Finder in it works all that well, so I use it on my Mac. There's this tree. You can see the tree on the left, and then you can see a database per directory on the right. And so I'm going to do a bunch of queries against that to show you what it will do. The first query, I'm going to just query against the entries table, and I'm going to do something simple like a regex, or I'm going to do something like find me all of the files that are not zero. So that's what the bottom table is. And so it's really simple to do these things. You just say select, path, name, user, mode, whatever field you want to get, format it any way you want, and put anything in there you want to put in there for size bigger than whatever, date older than whatever, combinations of things. You can do this. And again, what this does is this forks a whole bunch of threads, walks this thing breadth first, goes all the way down, only the parts you can see, until it gets to a roll up, and then it just does it all at once. And so that's how it works. Let's go on to aggregating. So one of the things you obviously want to do is aggregate. You want to find, what are the top biggest files, or what are the users that you use the most space or whatever. And so you can do these interim databases and aggregate. You can start anywhere in the tree. So when we do that roll up, we roll up everything to every directory. And so every directory has everything in it and everything below it. And so you can start anywhere in this thing. You can start clear at the top, or if you're only looking in this place, you can start down there. You can control how many records, of course. This is standard SQL for, I only want to see the top 3. You can stack statements. You can do multiple queries in one pass, as many as you'd like. The summary record is kind of interesting. Notice that what I said to do at the bottom there is find me all of the directories that have more than 0 total extended attributes on files. And it does that for you. The tree summary is very super interesting. Why? Because all the information from everything below you is in that one record. And so if you went and said, so normally what you would have to do to find out information about how much space is used in a tree below you, you would type in du-k, and it would walk forever. And 6 weeks later, when it's done, it would come back and say, yep, you use some number of exabytes or whatever, and this user used that, whatever you wanted to find out. So this does it, and it does it in sub-millisecond. It's one record it has to go get. It reads one record, and it already has this information. So it's a week or a millisecond. You can pick which one you want to use there. Extended attributes, yes, it does extended attributes. So if you're a POSIX person and you put extended attributes on files, you can query the extended attributes and look for text strings in them or whatever it is you chose to put in there. It has group by, so if you wanted to say, find me, I'd like to list a list of how many PDFs I have and how many Excels I have, and if you want to group it by that, you can do group bys. Here's an example. We've been in business for a really long time. We've had computers for a really, really long time, something like 70 years. We have a lot of history. We scanned about 1 million pages of our history. We OCR'd it, and we put it into a textual database and hooked it up so that you can do a query. So this query might be something like, find me all the files that are bigger than a bread box and older than whatever in this sub part of the tree, and oh, by the way, I'd like to know if matches is Grider is within 4 words of Seagate. You can do this query, and it will do it, and it will obey POSIX, so it will only give you back the answers you're supposed to see. So it's kind of turned in from this query engine into a Swiss Army knife of data curation. People are talking about curating their data, getting it ready for AI. How are you going to do that? Well, I've got 10 billion objects I've got to go get ready for AI. I need a way to do that. This is interesting. What this does is it will run a command for every file or every directory it encounters, whatever you tell it to do. And you can put the directory or file name in there. You can run any command you want to run. And so you can notice that what I did at the very top there is I said, go run this command called intop for every file I find. And I want you to run word count -c. Anybody a Linux person and they type in wc-l or wc-c all the time? It basically counts the number of characters in a file. And so by this one query, I said, go run word count -c on every file you encounter, or it could have been every file you encounter that's bigger than a bread box or whatever, and it will return that integer back in your query, and you can have that to deal with as you like in your query. And at the bottom one, I did string op, so that's intop. It returns an int. The next one returns a string. I said, go run word count -c and just print out what you have. Just tell me what that is. Don't get the integer, just tell me the whole string. And so it does that. So a data scientist could easily just go say, find me all the files that are bigger than this and older than that and have this in the name and this in the text. And oh, by the way, I want to run these commands on them. And it will go do that. It's also interesting that that runs a command for every directory or every file, which basically returns a string or an int. What if you wanted to return a table? What if you wanted to run a command that will return a table? What's an example of that? Well, this example I made up was I want to run find on every directory that I go through. I want to run find piped into cat, and I want to just cat it. And these were a bunch of CSV files. And so I said, I'd like to take all those CSV files and convert that into a table dynamically that I can now query with SQL. And so if you think about that, if you have 400 million CSV files, a really good friend of mine is sort of my position at JP Morgan, and they have more CSV files than I have objects, which is a lot, right? And they want to do stuff like this. They want to say, well, I have these CSV files, and I want to turn those into databases so that I can do something with them. And this will do that, and it will do that for the price of nothing. And so it's pretty powerful. It's pretty interesting, this kind of building a virtual table out of a command. A really cool example is nearest neighbor. We're all engaged in nearest neighbor up the wazoo today because how does machine learning work and how does AI work? Well, you want to find the vector that's the closest to the vector of the question you asked. That's a nearest neighbor query. It's not nearest neighbor greater than or nearest neighbor less than. It's nearest neighbor. Which ones are nearest to me? And so I said, how would you do that? You would do that by, remember, you've got this is how it's laid out, and you have these external databases that have vectors and links in them associated with the files, and you throw off a query. And I went through several iterations of how you do this, but I think this one probably here is the most interesting. Way I do that is I create a temporary database, and I go and I run the query, build a virtual table, and I execute get the CSV or that kind of thing, and build up the interim results, and then let the interim results say, okay, fine, sort it by whatever length, distance, whatever you want to do, and give me the top three. And so essentially this is an incredibly efficient way to do a nearest neighbor query. What I just said was this is a dynamic RAG. You could basically type in a query and say, make me a RAG with the only parts I'm interested in and only the things I can see. So if I take a model and I train it against the data that everybody can see, and I build a RAG for only the data that I can see, now I can ask that questions of that model, and it's only the data I was supposed to be able to see and only the stuff I was interested in seeing dynamically. And so it will build one of these for you on the fly just by filling out a, hey, make me a RAG, and here's what I'm interested in. Stuff that's older than this and bigger than that and has this text in it and whatever, and make me a RAG so that I can start asking questions of it. And so this was what turned on OpenAI. They went and said, my goodness, that's interesting, that's pretty powerful, we'd like to use that. This is the way we did AI. We just downloaded a model, yeah.
So you can sort of separate out what data set that you want to expose, but you still have to feed them to whatever is, creating the embedding sort of it.
You've had to have embedded it,
yeah.
and that's actually what this is. Okay. So we just went and got a Hugging Face model, process the text in chunks like normally you do, make chunk records with vectors in them. It's a vector table type in SQLite. This is all SQLite. And it embeds the vectors, builds an SQLite table out of it. You link it on a common field, file name, and all of a sudden you can do this stuff. Virtual tables are kind of interesting. We talked about virtual tables already. Virtual tables are useful if you want to use this thing in the Apache ecosystem or some other ecosystem. So let's say you want to treat this query you just built to run against this billion things in a huge set of trees, and you want to treat that like something you can go read from a Spark job or from a Presto job. If you want to allow that thing to enter into the Apache Analytics ecosystem, this will do that. You can basically say, turn this query into a virtual table and make that virtual table available to SQAlchemy. In this particular case, SQAlchemy is a Python thing that you can go build tables out of so that you can see them on the screen and that kind of thing. And so it fits into the Apache ecosystem instantly this way. You can also query it using DuckDB. If you're an analytics person, you know all about DuckDB, you think DuckDB is wonderful, and people that built it walk on water and all that kind of stuff. It's all good. GUFI can be seen the same way through as DuckDB as SQLite. It doesn't matter. But you get the added values that DuckDB gives you, and one of those is push-down analytics, which I'll talk about in a minute. What else would you want to do besides get a list of all the files that are indicated in the query you just did? You might want to go search through those files. You might want to present those files to people. There's a fuse that will take the output of your query and mount it for you. And so now you have a mounted file system of a view of the files that only apply to your query. And so now you can pull it up in your Finder or whatever favorite tool you have for looking at files of mounted file systems. And it only is the files that match your query. This is how we would use DuckDB. DuckDB has this ability to do push-down analytics. I could give you a nice talk about push-down analytics, but I don't have time. Essentially, you can push down the query to very close to where the storage is. This, you're pushing down the query to many, many servers that are running sharded parts of the subtree and get your answer back as fast as you would like. Anyway, I'm late. I probably should get off. Hopefully you can see that the thing is pretty darn powerful. The price is right. It's Berkeley licensed and free. We run it in production and we fix it all the time. It got broken once really badly. Texas Advanced Computing Center, TAC at Austin, an NSF supercomputing site, had one runaway process that created 189 million directories inside of one directory. And we were having troubles indexing that, so we had to fix it. We fix it. If it's broken, we fix it. If there's stuff that needs to be used, that needs to be fixed, we will. It's embedded in 3 products today. If you get BGFS, they have this thing called Beehive. Beehive is this. They just take the code and use it. It's embedded in Luster's, in HPE's Luster product called Brindexer, although it's a fork and it doesn't have all the options this has. And then we're working with an AI company, a different AI company than I mentioned before, and they want to use it to build like vaults that are smart. Right, so you could drag your stuff into a vault, a folder or something, or a set of folders, push a button, and all of a sudden you've got a RAG for it, and it's your own private RAG. So anyway, there's administration. It works with many different kinds of file systems, POSIX, GPFS, Luster, HPSS. It'll extract stuff out of Robinhood. It's been around for a long time, so it's very stable. I'll probably give up now. So if there's any questions, I'm holding you from snacks. Yeah. How often do we update and how do we roll up the changes? That's a really super good question. Every file system has its own little secret tricks for how you get, what's been changed from it. Luster, for example, has the Luster activity log, and the Luster activity log was actually neutered, if you will. There's a light version of the Luster log so that you can track changes. We do that about every 4 hours. For other file systems, it depends on how volatile they are and whether they have any decent, usability features for pulling out what's changed. GPFS has this thing called the ILM, and it's a shadow inode table, and you can go walk it and figure out what's changed, and so that makes it pretty easy to do. There are some file systems that it's harder to do. HPSS is one of those. It's DB2, and so it's a little tougher to go figure out, but we've worked to try to make those things happen. So it's really dependent on that. It's dependent on, are the file systems, do they have the ability to tell you what's been changed? If they don't, it's pretty tough. Yeah. But isn't that true for all backup products and all those things, right? In fact, NetApp has an interface that you can use for this, that the backup products use to tell what's changed. All right. Thank you.